Okay, now let's talk about the inference. The inference for the two-stage least square estimators are very it's actually very straightforward because it is very similar to the OLS estimator. Okay, so so let's write down two-stage least square. We know it's equals beta plus n inverse I prime summation xi, right? And what we do, so this is the bias formula for the two-stage least square estimator, and we just move beta to here. So we have and then multiply by a square root of n. Right? And we put the square root of n here to combine with the n inverse here, and we have here. Right? So we have n to the power of negative half. Okay, so we have this guy and here. If you remember, basically, we are going to apply central limit theorem to this term here, to this guy, right? Just like in the OLS case. Okay, but here note that, so what we do first is we rewrite here to be x star, the linear projection. Okay, and because we know xi star is the linear projection of the xi hat. Sorry, xi star is the probability limit of x hat, the fitted value, and which is the linear projection. So we can rewrite the fitted value into the linear projection, with a small op1. With a small op1 here, right? Because basically we know x star is xi hat plus small op1. Okay. Okay. So to apply the central limit theorem to the second term here. So the second term here is quite straightforward. Let's see. Right. So n summation xi. Right, we can just apply central limit theorem. Will converge in distribution to a normal distribution of mean zero and variance xi star prime u. Actually here we already changed to here we already changed to xi star. Already changed to xi star. Right, we change all x hat. We change all x hat to x star plus op1. Okay. This is just by central limit theorem, right? By COT. Okay, and we know this guy equals u square xi star prime xi star. Okay. And because we know this guy actually converge to improbability to here, it converge improbability to the A here. So the whole thing, so we know the whole thing, two-stage disk beta should converge in distribution to a normal distribution with mean 0 and the quadratic form. Basically, we just multiply this thing by A inverse here, right? So we know there's a quadratic form here. Similarly, just like the OLS case, if we want, we can make an additional assumption, homoscedasticity assumption, and that will simplify the variance, the variance. Okay, so if we are willing to assume this guy, which a sufficient condition is that the variance of U given Z is a constant. Okay, so this is a sufficient condition. Right. So if you are willing to assume that, so homoscedasticity assumption, then we will have this guy. Okay, so the B matrix can be simplified to this guy here. Okay. Right. So under the two-stage least square 1 through 3, we can further simplify to the distribution to be a normal distribution with sigma square times n inverse, right? Because A inverse B inverse will become A inverse times A times A inverse, right? And the A inverse and A will be cancelled out. Will be cancelled out here. So that's it. The last thing we needed to do is, well, we still needed to estimate the standard errors, right? So there are some unknown parameters here, right? So sigma squared is unknown, A is unknown, but A is actually, well, we already know how to estimate A, right? A is just here, because A is just the probability limit of this guy here. Right? So we just use this as an estimator for A. So that's not very important. The tricky part is about the sigma square. Okay, so to estimate the sigma square, first we need to define the two-stage least square residuals. So that is yi minus xi times beta hat two-stage least square. Importantly, these two-stage least square residuals are not the OLS residuals from the second stage regression. So if you run a regression, if you run a two-stage least square by hand, so you run the first stage, then you plug in and regress y on x hat, the standard errors or the residuals from the second stage are not correct. Okay, you should not use that to do inference. To do the inference, to get the correct residuals, you actually needed to plug in the two-stage least square estimator or two-stage least square estimates and get the residual from using the original x, not the x hat. Okay, then we can easily estimate sigma square using the same procedure, the same estimate like in the OLS. We just use the two-stage least square residual here, and we can estimate the sigma square. Again, the K here is a what we call like a finite sample correction or degree of freedom correction. Okay, so then will be our homoscedasticity variance for the two-stage least square estimator. Okay, and note that this actually looks pretty similar to the OLS one, right? Except the OLS without the head, here we have the head. Okay. Similarly, we have the heteroscedasticity robust variance. Again, it's almost like the OLS one, except we have a head here, right? Right, the OLS one is like minus k and x prime x inverse x prime Yu-Wei prime x prime x inverse. Right, so without the head. But they have exactly the same formation like the OLS estimator. So in fact, we have actually a similar efficiency condition here, efficiency result here. Under the two-stage least square 1 through 3, two-stage least square is the best linear IV or instrumental variable estimators using linear function of z. So that means, so it's very similar to the OLS efficiency result, but note that it's actually less efficient than the OLS estimator, because you can see that here. You can see directly that this guy will actually be smaller than this guy, right? Because x prime x will be larger than that, the x prime head x head. So the whole thing, because there's inverse, so the OLS estimate, the OLS variance actually will be smaller than the IV estimator variance. Okay. So what does that mean? That means, so two-stage least square is the best linear IV estimate, but OLS estimate is the best linear estimator, right? So if the x is exogenous, you should definitely use the OLS. But if not, then when you have to use IV estimator, the two-stage least square actually is the best linear IV estimator. And conceptually, it's because, intuitively, it's because the two-stage least square, it picks the most efficient way to combine. So the two-stage least square estimator use the most efficient way, the most efficient linear combination of the instruments, because it uses the linear projection, which is the most efficient way. So that's why it is efficient. So for example, because we make x star equals, let's say, delta 0 plus delta 1 z1 plus delta 2 z2, right? That's the linear projection. So the efficiency result here saying that's actually better than x tilde that we just use, let's say, z1 plus z2. This is also a linear function of z, but this is not the linear projection. And the efficiency result here saying using x star will be better than using x tilde. So that's actually what the efficiency result here saying. So the two-stage least square using linear projection, which is the best linear combination of the instrument. Of course, we are talking about only linear here, so there actually exists more efficient IV estimator based on nonlinear function of z. For example, later it will talk about the GMN, generalized method of moment. And in GMN, you can actually get even more efficient estimator using nonlinear functions. One drawback, of course, is that there's no free lunch. To get more efficient estimators, in general, you need to make more assumptions. Okay. Okay, so let's stop here.